Hey guys, hello everyone and welcome to the channel. So this video is going to be about all the questions from your quantum chemistry as well as from your molecular spectroscopy of your December 2018 CSIR NET exam. So why I'm making this video, why I'm solving all these questions for you, because I just wanted to tell you guys that these topics are not that difficult. Okay, although many of the students, especially from the bio background, they don't attempt these questions, they don't read about these topics, they think that this is very much complicated, but it's not. Especially for this particular exam, these questions are very direct, very easy. Okay, so I'll try to explain you guys with the best of my knowledge. I'll try to make you guys understand that how and what logic you can apply to solve these questions easily. So this video is going to be around 30 minutes video, so it's not going to be that much large. I have taken around 9 questions from the whole paper, 2 marks and 4 marks both. So I just hope the explanation will be fine for you guys, will like the explanation. If you are new to this channel, please subscribe to it. I usually come across, like I usually bring new videos for you guys, for especially for your CSIR net as well as for your GATE exam. And if you like this video, please give it a big thumbs up. And if you want to ask anything related to the video, related to the question, you can ask me in the comment section. I'll try to answer you guys over there. Fine. So enjoy the video, watch it carefully, and understand it carefully. Right. Fine. So we'll be talking about this particular question over here. It says that according to the uncertainty in the position of moving electron is 100 picometer, the uncertainty in its speed is closest to. Okay, so they are asking you about the uncertainty which you get for its speed. Okay, that is its velocity. Now we'll use Heisenberg uncertainty principle to solve this. So it says that delta x into delta px is equals to h upon, or it's greater than or equal to h upon 4 pi. Okay, so that's what your Heisenberg uncertainty principle tells you. So now this momentum px is your momentum in your x direction. You can write it down in the form of product of mass and velocity, so it can be written at like this. So you have delta x into m delta v, so and that will be greater than or equal to h upon 4 pi. So you need to find out this. Okay, this is the thing which you need to calculate. Now your delta v is like that will be approximately equal to h upon 4 pi into delta x into m. Just put the values over here from the question. So the values are given to h is equals to 6.6 into 10 to the power minus 34. That's given to you in the question. 4 you know, pi you know, 3.14. Delta x is given to you as 100 picometer. 100 picometer in meter will be 100 into 10 to the power minus 12 meters. And mass is given to you as 9.1 into 10 to the power minus 31. When you will solve all these things, okay, I'm not going to solve and all, but you can just solve it out. Okay, just 10 to the power if you just calculate. Rest of the things you don't have to do. So if you just calculate 10 to the power, you will get something around your delta v will be approximately equal to 6 into 10 to the power 5. Okay, meter per second. So that's what the uncertainty in your speed will be. So your option number 2 becomes your correct choice. Okay, so that's how it has to be done. Now let's take this particular question over here. The second one, it was asked that the spectrum of sodium atom has closely separated doublet at 16956.2 and 16973.4 centimeter. The higher energy transition is due to. Now they are asking that why this energy transition is higher over here. So basically this is your sodium atom. You all know that the electronic configuration, the last valence shell electron is in your 3s1, right? So your transition will take place basically from your 3s to your 3p orbital. Okay, from 3s to 3p, your transition will basically take place, like the absorption. Okay, so that when the absorption will take place, so it will be from 3s to 3p. But over here they are talking about the transition which is emission transition. Okay, so they are not talking about the absorption transition. So it will be like that. Okay. Now because we have one unpaired electron, whether it goes from s orbital to p orbital or from p orbital to s orbital, you will just have one unpaired electron. Now if you have one unpaired electron, so that means your spin multiplicity, that is 2s plus 1, that becomes 2 into 1 by 2 plus 1, that becomes 2. Okay, so your spin multiplicity becomes 2. So that's why you have 2 over here in all the options. Fine. So now you just need to find out the value of j, that from where the thing will happen. Okay, your term and j value. Okay, so your j value your J value is equals to L plus S. Okay. Now, since the transition is being done from p orbital, the electron will also lie in the p orbital. So your p orbital can have three values of L. Your L value can be either 1, 0 or minus 1. If the electron resides in 1, then your J value becomes 1 plus, so L is 1 and L is half, sorry, S is half, so 1 plus half, that is 3 by 2. Also your J value can also be like, if the electron resides in 0, then your J value becomes 0 plus half, so that time your J value becomes 1 by 2. So your p orbital, basically the electron, if the electron resides in p orbital, it can have two values, that is 2p3 by 2, or it can have 2p1 by 2. Now which one will have higher energy among these two? So obviously this one will have higher energy. Why? Because over here the J value is more, so this one will have higher energy. What about the electron when it will reside in s orbital? When the electron resides in s orbital, in that case S is having value 0, L value 0, and one electron is over here, so J value will be 0 plus half, like L is 0 and S is half, so it will be 1 by 2. So the ground state, or the where the electron will be in s orbital, at that time it will be 2s 1 by 2. Okay, this 2 comes from the spin multiplicity, remember. So in spin multiplicity is not getting changed. So if I if the question says that the higher energy transition, there the transition will have higher energy. So the higher energy transition will be happening when the transition will take place from the highest possible energy state to the lowest possible energy state. So this one is the highest possible, okay, and this one is the lowest possible. So that's why when the transition will be done from 3 to p3 by 2 to 2s1 by 2, that will have highest energy. So that's why your option number A becomes your correct choice. Remember, over here they are talking about the emission transition, not about the absorption transition. So that's why energy, the transition is being taking place from the higher to the lower. Fine. So that's why this answer will be correct option. Okay. So remember, in the question it says that the higher energy transition is due to the first one. Okay. So this is how this question has to be done. Let's take some more question and see that how they have to be done. Fine, let's take this particular question. It says that the third and fourth line in the rotational Raman spectrum of CO are separated by 8 cm inverse. The CO bond length is given by. Okay, so to do this particular question, first of all we need to know that the distance or the difference between the third and fourth line of, or between the two lines of your Raman rotational spectrum is actually equal to 4b. Okay, so 4b is the difference between two lines. Now 4b, the value of 4b is given as 8 cm inverse, so we can write it like 4b is equals to 8 cm inverse. So what is the value of b then? So b is equals to 2 cm inverse. Okay, so let it be the equation number 1. Now we all know that b is equals to what? The value of b. B is a rotational constant and its value is equals to h upon 8 pi square IC, right? So this is the value of your b. Okay, so its value is given to be 2. Now I is the moment of inertia, that is equals to mu r square. So we will put it over here. I is equals to mu r square. So let's put it over here. So now this b will become actually h upon 8 pi square mu r square c. Now this r is the thing which we need to calculate actually. Okay, so this r square will become h upon 8 pi square mu bc. Okay, so this is how it will become. Now just put the value of b over here, and what will be the value of r? So if I put b is equals to 2, so 2 into 8 will become 16, right? So this will become under root h upon 16 pi square mu c. So if you look upon to the options, so option number A is your correct choice. So it was very simple question from your molecular spectroscopy. It was very simple, direct question. Fine, let's take this question. This was also one of the very easy question asked from your quantum chemistry. Okay, very easy question. It says that the Hermitian operator among the following is. So which of these is a Hermitian operator? Now if you have watched my video on Hermitian operator, there this is the link for that. I'll give you link for that over here. You can click on this card and you can watch that video if you haven't watched it. So over there I have explained all these Hermitian operator in detail. One of the postulate of Hermitian operator which is very important to know is that all the physically observable quantities, okay, all the physical observable quantities in your classical mechanics are actually Hermitian operator in the quantum mechanics. Like your position operator is Hermitian, then your momentum, okay, both kind of momentum like linear momentum and angular momentum, both momentum operators will be Hermitian. Your kinetic energy operator is also Hermitian. So all these operators are Hermitian. So in these options you just have to identify, okay. And if it is not given, then the criteria is this, that if you have a dagger is equals to a, if you get like that, then this is the condition for a Hermitian operator. But over here you don't have to do that, you don't have to solve it, you can just do it with the help of postulate. Now momentum, linear momentum operator value is given by this, that is the linear momentum operator, you all know, that is minus I h cross dou by dou x, right? So this particular term is actually equal to your linear momentum operator in x direction. So this will obviously be a Hermitian operator. The others one over here, nobody of them is a operator, is a standard operator. So that's why your option number 2 is your correct choice for this question. So you don't have to do anything, no solution, no mathematics, just with the help of postulate you can solve this particular question within seconds, okay. So that's how this question has to be done. Let's take some more questions and see how they has to be solved. Fine, so we'll take these questions from quantum chemistry. These are very direct questions from quantum chemistry, you don't have to do much of it. If you have watched my videos, you have attended my class, especially those special classes on an academy, those live classes plus on an academy plus, then you could have done all these questions easily, okay. So yeah, direct questions, no mathematics is involved over here, even bio students can also attempt these questions, okay. So the first question over here says that the difference in average values of position for states n is equals to 1 and n is equals to 2 for a particle confined in one dimension box of length L is, okay. So you have a particle in one dimension box, you all know that how this one dimension box problem actually works, and over here you have two different states like energy value n is equals to 1 and n is equals to 2. Now remember one thing, that when you change these states, the energy value changes, you have different energies for, because the energy is like this, n square h square upon 8 ml square. So the energy changes with the change in value of n, with the change in state, but the value of position does not change, okay. So the position value remains constant for different states, so that does not depends upon state basically. So over here it says that the difference of average values of position for different states, you have two different states given to you. So the difference in the energy, the average value of position over here, since the position will be same for both the states, so if you take difference of them, so you are subtracting the same value from the same thing. So that means what you are going to get, you are going to get 0 over here, okay. So remember this thing, I am once again repeating that the energy of a particular particle inside one dimension box, it depends upon energy, it depends upon the state, according to this particular formula over here on the screen, this one, but the position of the particle is independent of the state, okay. So fine, so this is how it has to be solved, okay. So your option number 4 is correct, 0 is the correct option. Talking about this question number 104, these all of questions were of 4 marks, okay. So remember 4 marks, how easily you can score, you just have to like practice questions, and if you know the thing, you can easily score 4 marks. So it was very simple in your December 2018. Fine, let's talk about this one. It says for a one-dimensional harmonic oscillator perturbed in x cube potential, the sum of the first order and the second order correction to the ground state energies. Now those students who are attending my plus classes, they all know I have taught this quantum chemistry in much detail over there. All these shortcut tricks and all I have given to you guys over there. Those who are not attending that, I'll just explain in a very brief over here, that if you have x to the power n, okay, and if n is odd for simple harmonic oscillator, okay, only for simple harmonic oscillator problems, if you have n odd and you have x to the power n, then your first order energy correction
is taken to be 0. Remember this, okay? So your first order energy correction becomes 0 when you have x to the power some odd value only for simple harmonic oscillator. This is only applicable for simple harmonic oscillator, not for one dimension box, not for hydrogen atom problem. It is just applicable for simple harmonic oscillator. So remember this thing, okay? So your first order energy correction becomes 0. What about your second order energy correction? So there is a postulate for second order energy correction. Your second order energy correction is always, whenever you do second order energy correction, that is always negative. Why is it so? You can do it from the formula of energy correction. Over there, always the energy correction is being done in the denominator. You have E2 minus E1. Okay, so energy of the second term minus energy of the particle in first state. So always the energy of particle in first state is higher than the second state. So when you subtract that, you get a negative value in the denominator. So always second order energy correction is negative. Okay, so this is also one of the things you need to remember. Now, if you add all of them, so it says that the sum of first order and second order energy correction. So if you add both of them, that means total energy correction, if you want to calculate, ET is equals to sum of first order energy correction and second order energy correction. If you add both of them, you are adding 0 with some negative value, so obviously you are going to get a negative, right? So your total energy correction will be negative. So your answer first will be your correct answer. Okay, so see how simple it was. Although it looked little complicated, it was looking little complicated. Many students left this question also just by reading it out, but it was very simple. Okay, so that's how it has to be. Understood? Let's take some more question and see how they have to be solved. So over here in this particular question, this was question number 103, was asked for 4 marks. It says that a molecule AB2 shows following IR and Raman spectrum. Okay, now first of all, I'll tell you that this question was direct from KL Kapoor. Okay, so if you have KL Kapoor, you can find this question directly from there. So it's a like totally copy and paste question from there. Okay, so now over here it says that we have different IR values and different Raman values. Now, if you know about the basic of your IR spectrum, you know that the higher IR spectrum is given for the stretching. So these two belongs to your stretching. Okay, so stretching, and lower IR belongs to your bending. Okay, so this is because of bending. So these two things you should know. And one more thing, that if a molecule is symmetrical, in that case in IR you get PR bands. Okay, while if the molecule is asymmetrical, you get PQR band. So over here, when you are stretching the molecule, when you are doing stretching, the molecule remains symmetrical. The molecules remain symmetrical. Okay, and when you are bending the molecule, in that case the molecule is becoming asymmetrical. That's what our data is telling. That's what our data is telling us. Now we have AB2. AB2 can be like this. Okay, sorry. It can be like this, or it can be like this. So these are the two basic possibilities of AB2. Now when you are stretching the molecule, let's say if you are stretching the molecule like this, symmetrical stretching in the same direction, so then it remains symmetrical. Okay, so this is symmetrical stretching, and you can do asymmetrical stretching like this. So in both the cases, when you are doing symmetrical stretching or when you are doing asymmetrical stretching, in both the cases the molecule remains symmetrical. Okay, the molecule remain linear. So in both the cases your molecule is linear when you are doing the symmetrical stretching. Now when you are bending the molecule, when you start bending the molecule, in that case what will happen now? So when you bend the molecule, so okay, so let's say if you have this one, in that case if you bend the molecule, so let's say this is bent in the downward direction, A will bend like that. So if you bend the molecule, the overall molecule remains symmetrical for this particular case. Okay, so for this particular case in bending also it remains symmetrical, whereas for this one if you bend the molecule it becomes asymmetrical. So for this one if you are bending the molecule it becomes asymmetrical. That means our molecule is actually linear and asymmetrical. Okay, so our molecule is linear, that is what we get from this PR bands, and it is asymmetrical, that's what we got from the bending modes. Okay, so what will be the point group now? we got that the molecule is linear and asymmetrical. So for a linear and asymmetrical molecule, the point group we get is C infinite. So option number C will be correct for this. Okay. So it's very simple. You just need to know about the bands. So remember this thing, that for the linear molecule, your IR bands are PR for stretching frequency, for symmetrical stretching frequency. Okay. And if you want to understand this in more detail, please follow this KL Kapoor book. Over there, this topic is given in much detail. Okay. And this actually is data given for your N2O molecule. So yeah, that's how the answer will be C infinite V. So this was how this has to be solved. Let's take some more questions and see how they have to be solved. Okay, let's take this last question of this particular video. This question was asked for 4 marks from Huckel molecular orbital theory. So it was kind of application of that, and it was very simple to approach this question. Question looked quite different, but it was very simple. Okay, so it says one of the Huckel molecular orbital for 1,3-butadiene is, so it's given in the phi form. So phi is 0.6 chi1 plus 0.37 chi2 minus 0.37 chi3 minus 0.6 chi4. Okay, so now you need to see that where are nodes. Okay, you need to just find out the number of nodes, and then you have to find out that the energy of this orbital in terms of alpha and beta. So it's totally simple. Okay, it's very simple. I'll just explain you how you will do that. First of all, just find out the number of nodes. Okay, so I'll just give you a basic knowledge of it. So if psi is the wave function for this, so it will be like this: C1 psi 1 plus C2 psi 2 plus C3 psi 3 plus C4 psi 4. If this is like that, you have 0 nodes. Okay, you have 0 nodes over it. Now if you have psi is equals to C1 psi 1 plus C2 psi 2 minus C3 psi 3 minus C4 psi 4, in that case we have 1 node, because sign has changed from here. Okay, don't count the number of sign change, you just have to see that from where the sign has changed. Okay, if it is like psi is equals to C1 psi 1 minus C2 psi 2, okay, then you have plus C3 psi 3 and then minus C4 psi 4. In that case you will be having 1, 2 and 3, so you have 3 nodes over there. Okay, so this is how it has to be done. Now if you relate this with this particular equation which is given to you, it has 1 node, right? It has 1 node. How it will look? So if you want to draw this, it will look something like this. Okay, so if this is the orbital, I'll show you that how it will actually look. So you have 1 node for this, so you will be having one of that. This is your 0.6 chi1, then you will be having 0.37 chi2, okay, and then you will be having minus 0.37 chi3, and then you will be having minus 0.6 chi4. Okay, so where the positive signs will be here, this will be the shaded one, are the positive nodes. So this is how they will look like. Okay, so over here, how many nodes we got? So we got 1 node for this particular molecule. 1 node means, now in the molecular orbital, if you see, so 1 node means you will be having for 1,3-butadiene, you will be having 4 psi, right? You will be having 4 molecular orbitals, psi 1, psi 2, psi 3, psi 4. 1 node means I am talking about psi 2, right? I am talking about psi 2 because psi 1 will have 0. The lowest one will have 0 nodes. First one will have second node, and psi 2 will have one node, psi 3 will have 2 nodes, psi 4 will have 3 nodes. So it's like that. If you have studied this thing, you know about it, right? Now let's talk about the energy order. So if you write down the energy order, energy value, so this is let's say the lowest one, psi 1, then your psi 2 is there, and you have psi 3, and then you have psi 4. So if I write down the energy values, so for psi 1, the energy value is like alpha plus 1.62 beta. Okay, that's the value for psi 1. For psi 2, it's alpha plus 0.62 beta. For psi 3, it's like alpha minus 0.62 beta. And for psi 4, it's alpha minus 1.62 beta. So these are the values in the terms of alpha and beta for these orbitals. Okay, so you can arrange them in the order of increasing, value. Okay, so this is how they have to be arranged. Now we got that this particular orbital is actually our psi 2. We are talking about psi 2. So psi 2 is having energy in the term of alpha and beta like this. So alpha plus 0.62 beta. So option number B is the correct option. So just with the help of basic knowledge of this particular Huckel molecular orbitals, you can answer this particular question. Fine. So this is how you can do questions from quantum chemistry, from your molecular spectroscopy so easily in exam. They are not that difficult. It's just like you have not uh, practiced much question. That's why you like you feel problem while solving, right? But it's not at all difficult. So that's all for this video, guys. I hope you guys like this video. If you guys like this video, please like give it a like, and if you are new to this channel, please subscribe to this channel. I usually come with videos like this for CSIR NET and GATE exam, and if possible, do share this video with your friends and those students who are preparing for this. So that's all for this video, guys. Thank you so much for watching. Have a great day. Bye bye.